So in this video, I am designing the portal gears. I left this alone for the weekend and realized that I had a critical error on the sizing and the spacing of the gears. Basically, the gears were too big for the housing and I wasn't going to be able to fit an O-ring, and there wasn't enough meat for the counterbores to bolt the outer portal box to the upright. So rather than redesign the entire thing from scratch, I just decided to increase the clearance that was available to me on the portal box and make a cut on the part that would interfere with the wheel. I also reduced the gear ratio from 2 to 1 down to 1.55 to 1. So I ended up with a 7-inch diameter output drive and a 4.5-inch diameter input drive. So I got those dimensions from just what was going to be able to fit at its maximum in the housing. And I got the ratio from a diagram that I found on 74 Weld. As far as I can tell, Hummer H1 and Humvee portal boxes are 2 to 1, and so are Unimogs, or somewhere close to that. But for the race application, the 4-gear race portal, they run between 1.3 and 1.6. So I figured 1.55 was probably fine. I would prefer to keep it 2 to 1 just because the tires for this project are so big. I'm running the Mickey Thompson 58-inch Baja Pros, and those are the biggest tires available for an application like this. So the greater the gear reduction, the better, but in this case, it was a space constraint. So right now what you see is I'm working on the gear profile design. So it's just a simple boss and a simple cut with a circular pattern. And what I'm about to realize is that the gear tooth profile that I have is way too fine. I'm going to basically triple every dimension here to get it to match what I see in the diagram from 74 Weld. It's just a big, beefy gear tooth. It's as big as possible. And so the trick with these gears is you want the tangents to be touching, but you want the gear teeth to overlap the tangent so that you get engagement. When I originally designed this, I didn't have that in mind. So there was only enough clearance for the tangent and not enough clearance for the teeth. So fixing all of that right now. And now I have an input shaft, an output shaft, and a matching idler shaft. So the first thing that I need to do is increase the clearance on the portal box outer shell so that I can have enough room for an O-ring to seal the assembly together and keep oil in there. And also make sure I have enough room for those big 3/8 inch counterbores for the 12-point screw hardware that I'm using to keep the whole assembly together. So I was playing around with different gear ratios, trying to get as close to 2 to 1 as possible, but I settled on that 1.55. And that made the gearing really easy because I could have a round number on the angle of the gear teeth and then match that spacing on the smaller gears with the same angle to make sure that the gauges are going to engage with the right amount of clearance. So the result of that extra clearance on the portal box outer shell was that the tall knuckle increased in width significantly. So what I like to do whenever I make a big change to a part that is largely done is I'll just roll that part back in SolidWorks in the feature manager and then roll it forward one by one to fix any errors. And that makes it a lot easier than, redesigning the part from scratch or chasing your tail on features that are all sort of interconnected. When you roll a feature set back, you're only editing one feature at a time in the sequence that it was built. So things are able to rebuild without error a lot more easily. So what I'm trying to figure out now is what kind of bearings am I going to use to mount these gears to the inside of the portal box. I wasn't originally planning on getting this detailed with the design. I was just going to leave it like a blank empty shell mock-up, but in order for this to all make sense and actually be machinable, I just need to add a couple of bearings, and it's really not that complicated. There's just 2 bearings per gear in this design. I'm sure in a real manufacturable high mileage application, I would need to do some more engineering on this, but there's so many good bearings in the McMaster-Carr catalog that I was able to find something that just fit perfectly. And that was this 6-inch outer diameter bearing. It's a tapered roller bearing, so it does good with thrust and radial load. And that's perfect for this application because there's going to be a lot of forces on that output gear. So now I'm just making the hub snout. So this is the piece of the output gear that's going to interface with the unit bearing and apply the drive torque to the wheel. And it's just a series of simple bosses and clearances for those bearings. And then I need to do the same thing on the tall knuckle to make bearing clearances for the input gear and the idler gears. Right now I'm just fixing some screws to make sure that they all match up properly. I realized I missed some screws here that I need to put on the outer shell. And then I had this strange offset there where these 2 holes weren't matching up, but I ended up figuring out why. Checking my thread depth. This is super critical in tapping design. So when you're designing threaded holes, a good rule of thumb is you don't want to go too deep on the threads. The rule of thumb that I like to use is your thread depth should be no greater than 4 times the diameter of the screw. So for example, if you have a 1/4 inch bolt with a 1/4-20 thread, your thread depth should be no greater than 1 inch. That's just a rule of thumb that a mechanical engineer taught me one time, and it tracks because the default thread depths in SolidWorks Hole Wizard are about that. So I usually like to keep those default whenever I can. So now I'm realizing I need some clearance on these teeth in order to clear some of the features inside the portal box. So I'm making these resolved cuts here where I'm basically cutting a chamfer around the entire radius of the part, or the entire perimeter of the part. It's just a lot easier than making 40 discrete chamfer features. Just make one cut. This feature that you see here is the O-ring groove. So there's a lot of rules when it comes to designing O-ring grooves. I always defer to the Parker O-ring manual. So they have the biggest catalog of O-rings available in metric and imperial. And they also have groove dimensions in there. So like there's a lot of things that you want to do with an O-ring groove. Like for example, you want the bottom of the channel to be radiused. You want the outside of the channel to be chamfered, and you want a little bit of a taper in there as well so you get good engagement. So like if you have a 1/16 inch O-ring diameter, you want the width of that groove to be 120% of the diameter, and you want the depth of that groove to be 80% of the O-ring diameter. Those are good rules of thumb. So now I'm just adding more tapered roller bearings for the output drive. I don't actually know if I need this second bearing. The guys at 74 Weld put a big snout on the end of it, and I don't know if they use a bearing on that snout or if they just grease it, but theoretically there would not be any load on that part of the output gear because you have one bearing on the outer shell of the portal box, and then you have another set of bearings in the unit bearing on the wheel. So there's your 2 constraints. I just added a third one because I had room for it and it looked stronger. And then on the input gears and the idler gears, what I'm realizing now is that I have the wrong diameter on there. It was 4 inches, but it was supposed to be 4.5. But I'm going to end up with a 3-inch OD bearing to capture both of these. And I need to make sure that the groove is the right height. So luckily I had enough room. I'm assuming a 1.5-inch input shaft on the axle. And then there's plenty of clearance there for the bearing to go in and capture the input and idler gears. So again, adding that tapered cut on the resolve and making sure that everything matches. And then SolidWorks is crashing, but we're okay. And so now I'm adding another bearing on the outer side of the tall knuckle because this input gear is going to have a really, really long shank to it because it has to go all the way from the center of the wheel to like 8 inches out inboard. And I need to constrain that part of the shaft because this is basically the drive input shaft. Whereas the idler gears, they're a lot simpler. They're just housed in the box. The only force on them is torque, and there's no radial or lateral force on them. So those can be, oh yeah, now I'm realizing I got the wrong diameters here. So I got to fix those. Wondering why those tangents don't match. I made them 4 rather than 4.5. There they are, 4.5. Increasing the diameter on those, double checking all of my gear teeth dimensions to make sure I have enough clearance. So I assumed a 0.35 gear width on the teeth, and then I have a 0.37 clearance between the teeth. And that's to make room for oil during the drive. And so you have engagement on one side, oil on the back side, and then you have a backlash of 350 minus 370, which is 20 thousandths, which I don't know if that's a lot of backlash or not. I don't know anything about gear design, but that's something that a real mechanical engineer would know a lot about. So I think that's good enough for a mock-up. So now I'm just making some lightweight through holes on these because before I made those cuts, that particular output gear was like 20 pounds all by itself because it was alloy steel, probably heat treated. But the guys at 74 Weld have a really great video where they explain all the different materials that are used, why they use 7075 aluminum, why they use, as opposed to cast iron, which is traditional for high volume automotive manufacturing, why they use heat treated steel on the gears, and their gears are unbelievably strong. So now I'm just making some snubs there to capture the bearings and checking all my clearances on everything. And we're getting pretty close to the end of the design. So the last thing that I need to do is make sure that I have all my chamfers in the right place, make sure I don't have any interferences anywhere, and look at every aspect of the design to make sure that it's the way that it's supposed to be. And so this final cut here, this is what I started with when I was saying that I just increased one of my constraints. So rather than making this thing 2 inches smaller than it needs to be, I just need to make a 2-inch cut on the top of that part that hits the wheel. So that made the design a lot easier rather than starting from scratch again. And it ended up working out really well. I just need to make some machinable features here. Again, I'm assuming that a part this big and complicated is going to be done on a 5-axis mill. And so with a lot of ball end mill operations. So what I'm doing is for all the big cuts, I'm using either a 1/2 inch radius or a 1/4 inch radius to assume a 1 inch ball end mill or a 1/2 inch ball end mill that can get in on all those weird operations. So there we go. That's the design.